Have you ever had that feeling that there's more going on than meets the eye? Like there's a whole invisible world passing right through you at this very moment? Well, you're not wrong. And today, we're diving deep into one of the universe's most fascinating mysteries, the cosmic ghost particle.
So, let's start with a number, 65 billion. Just let that sink in for a second. What do you think that is? It's not the number of stars in the galaxy, it's not the world population. It's something happening to you right now, as you're listening to this.
That's right, 65 billion. That's how many of these tiny particles called solar neutrinos are streaming through an area the size of your thumbnail every single second. They're passing through you, through the ground beneath you, through the entire planet, as if none of it is even there. Wild, right?
Okay, so what is this phantom particle? Well, it's called the neutrino, but its nickname, the ghost particle, is honestly a perfect fit.
And here's why it's so ghostly. It has no electric charge, so magnetic fields can't touch it. It has a mass, but it's so tiny it's almost nothing. And, get this, it only interacts with other matter through something called the weak force, which, as the name suggests, is incredibly feeble. It's so non-interactive that a neutrino could fly through a light year of solid lead and probably not hit a single atom.
Now, the story of how we found the neutrino is really cool because it didn't start with someone seeing something new. It started with a huge problem, a crisis really, that looked like it might break one of the most sacred laws of physics. So, back in the 1920s, physicists were studying this thing called beta decay. It's basically when a neutron in an atom's core turns into a proton and shoots out an electron. But when they measured the energy before and after the decay, something was off. Some of the energy was just gone. It had vanished. And in physics, energy can't just disappear. That's like rule number one. This drove everyone crazy. So a brilliant physicist named Wolfgang Pauli came up with this really out there idea. He suggested, what if the missing energy is being carried away by a tiny, invisible particle that we can't see? He even called it a desperate remedy, because he basically invented a particle that he himself thought would be impossible to ever detect.
And this just goes to show you how long science can take. In 1934, another genius, Enrico Fermi, built on the idea and gave the particle its name, neutrino, which is Italian for little neutral one. But it wasn't until 1956, 26 years later, that two scientists finally proved it was real. They built a huge detector right next to a nuclear reactor, which pumps out tons of neutrinos, and they finally caught the ghost.
So, you'd think, great, mystery solved, right? Nope. Just when physicists thought they finally had this ghost particle pinned down, a brand new mystery popped up. It turned out catching them was one thing, but counting them was a whole other problem.
You see, scientists built these amazing experiments to detect neutrinos coming from the sun, and their calculations about how the sun works were rock solid, so they knew exactly how many neutrinos they should be seeing. But they weren't. For decades, every single experiment came up with the same bizarre result. They were only catching about 1/3 of the neutrinos they expected. Where were the other 2/3 going?
And this chart just lays it all out. For every 100 neutrinos our models predicted the sun was sending us, our detectors on Earth were only seeing about 33. The rest? They had just vanished into thin air. It was a massive puzzle. And the answer, when we finally figured it out, was somehow even weirder than the problem itself. The neutrinos weren't actually disappearing. They were changing their identity. They were putting on a disguise during their trip from the sun to us. This amazing process is called neutrino oscillation. So it turns out there are actually 3 different flavors of neutrino: electron, muon, and tau. The sun only makes electron neutrinos, but as they zip through space, they actually morph back and forth between all 3 flavors. The problem was our early detectors were only built to see the electron flavor. So when a muon or tau neutrino showed up, it was totally invisible to the experiment.
And this is where it gets really mind-blowing. The laws of quantum mechanics say that for a particle to be able to change its identity like that, it must have mass. This was a bombshell. For decades, the standard model of particle physics, our rulebook for the universe, assumed they were massless. The ghost particles suddenly had weight. Physicists literally had to rewrite the textbooks.
Okay, so they have mass. But how much? I mean, just look at this table. An electron, which is already incredibly light, has a mass of about 0.511. Now look at the electron neutrino. Its mass is less than 0.000008. That's at least 500,000 times lighter than an electron. It is so unbelievably tiny that we still haven't been able to measure it exactly. So, we figured out where the missing energy went, and we found the vanishing solar neutrinos. But where else do these little shapeshifters come from? Well, it turns out they are born from the most extreme and powerful events the universe has to offer.
They are literally everywhere. They're forged in the nuclear hearts of stars. They're blasted out in unbelievable numbers when giant stars explode as supernovae. There's even a cosmic background in neutrinos left over from the Big Bang itself, filling all of space. And, yep, we even make them ourselves, right here on Earth, in our nuclear reactors.
So the neutrino has gone from being just a desperate idea to a confirmed particle to a shape-shifting mystery solver. But its story is far from over. In fact, it might hold the answers to some of the biggest questions we still have about, well, everything.
Think about it. That same ghost-like quality that makes them so hard to find is also their superpower. A photon of light can be trapped inside the sun for thousands of years, bouncing around. But a neutrino, it flies straight out, instantly, carrying a pure, unfiltered message straight from the core of a star, or the heart of an explosion, or even from the first few seconds of the universe. They're the perfect cosmic messengers. And that brings us to the biggest question of all. According to our theories, the Big Bang should have created equal amounts of matter and antimatter. They should have completely wiped each other out, leaving behind the universe with nothing. But obviously that didn't happen. We're here. Some of the leading theories today suggest that neutrinos might be the key, that a tiny difference in how they behave compared to their antimatter twins is the reason matter won out. So the next time you think about that invisible world, remember those 65 billion ghosts passing through your thumbnail. They might not just be visitors in our world, they might be the very reason our world exists at all.